Hello, this is a pretty quickly thrown together presentation, probably a part one of two or three, meant to try and discuss how the GPU operates inside of the Dreamcast. This is intended for people that are just curious, or maybe are writing some homebrew, or people that are writing emulators, which is where this really came from. Okay, let's just get started. So the first slide here, we are going to take a quick peek at the hardware on the Dreamcast. So we basically have the SH4 CPU here outlined in orange. Let's see if I can get my... No? Ah, I see. Okay. So we've got the SH4 CPU here. We've got Holly, which contains an interrupt controller. It's got a DMA controller. It's got the PowerVR based GPU as well. And then we have two sets of memory here. So in blue, we've got 16 megabytes of, I guess let's call it system memory. I forget the official name. But basically that is addressable, accessible by both the CPU and Holly, the ASIC. The bus lines that you can see here actually multiplex all the addressing and data lines and everything between these two. Okay. And then for, so both of those can read and write, I guess is my point. The VRAM modules up here, each of them are 2 megabytes, so you get a total of 8 megs of VRAM. And if we zoom in here, you can actually see the data lines too. Each module has 16 bits of data bus width, giving you total 64-bit access per clock cycle, if you're not refreshing and stuff. We'll visit in a later part why that works well and addressing modes and all that stuff, but I kind of just wanted to paint a picture that, you have two main devices. Both of them can access system memory, of which we have 16 megabytes, and we have 8 megabytes of VRAM, which is only accessible by a Holly. I guess it's worth mentioning that Naomi and the arcade configurations and some other stuff, there's also a 16 megabyte variant of this. Let's keep going. But on the console, you only get 8 megs. So I thought it might be instructive before we dive into what is tile deferred rendering on the Dreamcast. Let's look at what non-tile deferred rendering is. So this is usually called immediate mode rendering. And for now, we're just going to consider the PS1. So some earlier GPU, although Voodoo and some other ones from the era are also immediate mode renders. So what's immediate is that geometry that's requested to be rendered more or less immediately finds its way rendered into VRAM, into a frame buffer. So let's consider that the CPU wants to render a triangle. It's running through game update logic and then gets to basically let's paint the next frame. What it does is, at least on the PS1, it'll send an individual triangle one by one through DMA to the GPU. The GPU gets one of these guys, and let's say it's for this right here. The GPU is going to run a rasterization technique of some sort, and it's going to determine, these pixels, these pixels, these pixels, these pixels, all need to end up, getting shaded. And then once it's got a few of them that it can write to video memory, then it will do that. So it will write batches directly into VRAM here. One of the consequences of that is that if, let's say, a surface right here, this particular pixel that I'm kind of highlighting here, might have let's say 30 faces that are all kind of drawn on top of that pixel. Only the closest one, the last one, really is what you would like to draw. Everything else effectively got wasted here. And if it was drawn out of order and it was translucent, it was also probably blended incorrectly, because if you imagine painting, translucent materials, it only works properly if you kind of blend and shade them from back to front. So anyway, that's a caricature of how immediate mode rendering works. So you basically get a bunch of accesses for every group of pixels here between GPU and VRAM. Okay. Let's look at what tile-based deferred rendering is, which is a system that Dreamcast uses. So I know this looks like a lot going on here. There was kind of a lot going on in the PS1 GPU. We only looked at it at a surface level. And we're, of course, going to go into a lot more detail here in the Dreamcast. But let's get quickly into the tile-based part. So the first thing is that of this 640 by 480 screen here, this screenshot from Soul Calibur or whatever, it's logically broken down into 32 by 32 tiles. So we'll get into a moment why that is, but there's basically two passes. We're going to render the entire frame buffer, only considering a 32 by 32 region at a time. So in the first pass, we're basically going to find out, before we do any rendering at all, before we shade and any of that, we're going to figure out which triangles actually land into each of these tiles. And we're going to build a list for each tile. After we have built up those lists for every single tile, then we're going to render one tile at a time. So we're going to render this tile. And then once we're done rendering it, we'll write that into VRAM. And we can render this tile. And once we're done, we'll write that into VRAM. So to contrast with what we were doing, writing batches of pixels over and over and over, compared to the PS1, the Dreamcast is basically going to do all the work it can in a single tile and then shoot that over into VRAM all at one go. This is going to reduce a lot of memory bandwidth, and we'll see later. Also, it means that we need to do a lot less shading work because we only, if it's opaque geometry, we definitely only need to basically shade one pixel, do texturing once, and a couple of other cool things. But basically, I just want you to get the idea that there's sort of two passes. One is building the list of which triangles will actually end up in each tile. So you can imagine this tile has 1,000 triangles, this one has 900, this one has 1,100, whatever. Basically a list of pointers to the data that needs to get drawn in that tile. And let's go through this very quickly. So we kind of looked at this in the hardware. You got CPU, you got main RAM, you've got Holly, which I'm calling the GPU here. The GPU, among other things, has tile memory, which is basically enough buffer to describe the colors and the depths and stuff that it will occur inside of a single tile, which is 32 by 32. It's got rendering hardware, which we'll go into detail, and then it's got texture cache and parameter caches. Connected to the GPU, we've got that VRAM we were talking about, and it stores a number of different things inside of it, right? So there is the full frame buffer. So in Soul Calibur, this is a 16-bit per pixel 640 by 480 frame buffer. And while one's being drawn, another one's being displayed on the screen, another one also exists in memory that's being rendered to for the next frame we're going to show. There's all the textures on all the surfaces. Let me kind of hide this for now. There's all the polygon data that needs to get written somewhere so that the rendering system can actually look at coordinates and texture coordinates and everything. And then because we're making a list of which triangles will actually eventually be drawn in every tile, we also need to set aside some space for which triangles, which objects actually correspond to which tiles. All right, that's enough to go on. So that's a lot of work. In the Dreamcast, we have a whole bunch of tiles we'll see a little bit later, and there's a lot of determination of which tiles will get which triangles. In Dreamcast, it's not uncommon to have 10, 20,000 triangles, and you've got 300 tiles in the 640 by 480 arrangement. You're not going to do all of that and all of your work and everything else on the CPU. So there's some special hardware to help with this called the Tile Accelerator, or TA for short. One thing we have to mention is that the TA doesn't just have one list for every tile. It's got 5 lists, and we'll talk about why that is a little bit later. Maybe the only 2 that we really care about for this presentation, and in part 2 or 3 or something, we'll go into more detail on the others, is opaque and translucent. Opaque is going to be everything that's opaque, so no alpha less than 1. And translucent is going to be everything that has any pixels which have an alpha that needs to get blended properly. Let's just say so it has completely transparent parts, or something that is needs to get shaded and properly blended. One thing to mention is that tiles are always rendered in this order. You may not have something in one of the lists, but every tile will first draw its opaque content, and then its opaque modifier volume content, translucent, and so on. Okay, so we've got all these lists. What does that actually look like in terms of data structures and stuff? we mentioned all the things that exist there in VRAM. There are three main classes of data structures that the TA kind of thinks about and that we need to be aware of. One is the region array. So we'll look in a moment what that really looks like, but the region array basically is a description of the stuff. It's kind of like a control word that describes what's going to happen in each tile. So if we have those 300 tiles above, we're probably going to have 300 entries in the region array here. Could actually have more. That's a subject for more complicated rendering techniques and stuff in a later part. Basically, you can imagine this first one is like the top left tile. It will describe, basically, we'll get to it in a moment. But one thing that we'll have to do is point to a list of what is going to get drawn. Those lists are actually drawn in what we're calling the tile list data or object list. And in a moment, we'll see the exact data structure for that. Those can actually refer to each other. So the first one might list, let's say, 32 objects, and then there's more than that inside of the tile. So it actually, in its last entry, will end up pointing to another one. And then maybe that one even wasn't enough, so it'll point to another one. The second region array entry, its first list entry might be here, and then that can point to another. It's basically a linked list data structure, and inside of each one of these, what we have is the ability to say, this block refers to this triangle, this triangle, this triangle, and this triangle. And maybe that's all we have space for. So you've got tiles mapping to a linked list of all the different objects. And then the objects themselves are kind of pointers into the actual coordinates and texture coordinates and texturing modes and all of that stuff. Hopefully that will make a little bit more sense in a moment. The high-level rendering process, once you've got all these lists, is this. There is a Holly MMIO register that's literally called start render. And what you do is you either write a 1 or the most significant bit. I don't remember. And what will happen is the GPU will begin to iterate through all of the region array entries. So again, there will be like at least 300 in a full 640 by 480 VGA frame. So while we still have some entries that we haven't processed, we're going to operate on that one region array entry once, right? So perform region array entry work. There's a few things that will happen. There will be some flags that we'll see, which may allow, we may be asked to basically clear the Z buffer. And now we have those 5 different lists. Some of them may or may not be enabled. And we'll basically draw all the geometry that was pointed to by the region array entry. And then we may or may not, depends on how it's configured, flush the tile into VRAM. So if this is like the last pass of drawing, then after we've rendered everything, we want to push that into VRAM, into the Framebuffer, so that it can eventually get displayed on the TV, on the monitor. After you've finished every entry in the region array, then you're pretty much done. And there are a few different interrupts that are listed here. I'm just mentioning here. After the final content's been written into VRAM, you can get a interrupt from the GPU, so you know when it's done. You can point the display controller at the new Framebuffer data. Let's look a little bit more in detail at the region array, since that's sort of like the highest level data structure thing that we need to worry about. Here we're going to look at just the first, 36 or something entries in a capture from the intro animation to Soul Calibur. We can see here is basically its position in the region array, its location on the screen in pixels, some flags, which we'll describe in a second, and then these are pointers in VRAM, addresses in VRAM to list data that needs to get rendered for that tile. So you can see this first tile probably is at the top left of the screen, and it points to some opaque data, some opaque modifier volume data, which without us going into it basically is for shadows, translucent data, and then something called punch through, which we'll also go through in a later part. There are no translucent modifier volumes. So while there are 5 lists and the tiles can describe content for every list type. If you don't have anything, you basically can put I don't have anything pointer in here. Now the flags, what's interesting here is there's a few different things that you can control. So you can say, in this tile, I want to have geometry sorted in the z-axis for me. So this is like a unique feature of the Dreamcast, not just Z buffering, but to literally sort on a per pixel basis all the geometry and then correctly shade and blend from back to front. That is a feature that you can enable with a particular bit in the control word of the region array. We'll get over here in just a second, a little bit more detail. Like I mentioned before, one of the first things that happens when you operate in a region array is you can basically, with a single bit, configure that you want the tile to be cleared. That will do a couple of different things. One is that it's going to set a Z buffer to a background depth, which is configured via MMIO register. The other is it's going to set something called the ISP tag buffer to the background plane. We'll look at that in a moment. The last thing is after this flush flag, basically after everything has been drawn here, you can specify by providing this flush bit that you want this tile data to get written into the Framebuffer in VRAM. There are cases, for instance, where you don't want to clear, you don't want to flush. You may not flush, as an example, if you are drawing twice on a tile. In another part in this series, I guess, we'll look at how you can do multi-pass rendering, which requires rendering content into a tile multiple times. And in that case, you only necessarily want to write into the Framebuffer on the last pass. If you have 3 passes, it doesn't make sense to write it the first 2, maybe. Another quick observation, which is detailed in the so-called like architecture Bible for the Dreamcast, is that it doesn't iterate over the screen from left to right, row by row. Here they're actually going sort of down the screen, and then they go over 32, and then 64. For caching reasons, this is detailed to be a slightly more efficient way to render. So what does a region array entry actually look like? It's not clear from here how large a region array entry is, but this is, without getting into the literal bit and like bit packing and everything, the region array entry is basically 6 32-bit words. The first one is just a control word that specifies, is this the last region in the array? Which is actually how you know when you're done. There is no like length or region array entry count register or anything. It's just, is the last region bit set? If so, then when we finish this, we're done. There's the bit that I mentioned about clearing Z. There's the bit that I mentioned about should we ask the GPU to sort every pixel for us? And the opposite of that, by the way, is you can say, I've already pre-sorted the data. You don't need to do the relatively expensive automatic sorting function. And then there's a bit for flushing. And then there's a description inside of this control word of actually where the region exists on the screen physically. The rest of these 5 pointers are effectively addresses in VRAM where the first bit of the list data would be for like opaque objects, translucent objects, etc. If the highest bit of any of these pointers is set, it implies or it indicates that the pointer is invalid. So if I was only drawing opaque list, then that bit would be a 0 here, and this would be a valid address. And it would be a 1 in the most significant bit for all the others, just indicating that there's nothing to access, nothing to look at. Okay. A little bit more into the data structures. So the object list is what I call, I'm not sure if it's a standard wording, but what I call fat linked list pointers, fat linked list data structure. So you've got the region array, which basically we're going to have 300 of these, 1 for each tile on the screen. And it's got a bunch of pointers. What do those point to? They point to these object pointer blocks. So let's imagine that the nth tile needs to render some opaque geometry. This pointer will point to somewhere in VRAM, and the content there is going to look like this. It's going to have basically n entries, which is configurable through an MMIO register called TA-alloc control. And basically, the GPU will go through all of these, and the TA, one constructing it, will basically be filling in this data. If you ever need more than one, then as you can see in this example here, it's very frequently you'll see that the last entry of an object pointer block in OPB will actually point to the next OPB, and that's how this can kind of continue onward and onwards. For the ones that aren't links to other object pointer blocks, each one of these effectively points at the actual polygon data. So that is very useful because you can imagine a triangle might span many, many tiles, and we don't want to duplicate that per tile. So multiple object pointer block addresses from different tiles, from this tile, from this tile, from this tile, they can all point at the same polygon data through their OPBs. And the entries that can actually show up inside of an object pointer block, there are 4 of them, 4 different kinds. The GPU supports a triangle strip, which is basically going to point at the first of a series of triangles that make up a triangle strip. And it also has a 6-bit mask, which lets you pick out which of those 6 entries it actually should render from that base address. So it could be the first one, it could be all of them, it could be, here's the pointer to a triangle, just draw the first one and the 5th one. Those are the only ones that overlap this tile. Similarly, there's a triangle array, which is just giving, the address of the first triangle, and then it says draw, a contiguous number of triangles out of this polygon parameter data list. Quad array, so typically for sprites, the Dreamcast always also supports quad rendering, and this is otherwise just like the triangle array. And then, of course, a tile, like we mentioned, is if these have like 32 entries, I'm definitely going to need more than 32. So it would have, for instance, 31, and then the last entry would point to another block, and that's how you can get sort of an arbitrary number of things to draw per triangle. There's also a bit inside of OPB link. And the actual, packed bits of this control word, you can specify this as end of list. So if the GPU ever reaches this, triangle, 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 and then it gets to a link that has a end of list flag, then it knows it's done. This triangle is completely done. Cool. So how do we use the TA? That's like almost everything you would want to know at a high level about what the TA is and how it organizes data. How do we actually use it? How do we invoke it? So there's a few things. This is not going into super detail. I'm not showing a lot of the arrangement in VRAM and everything like that, but basically you need to do these steps. So the first is to configure a pair of registers TAOL base and limit. Basically says, where will the object list data, so those object pointer blocks, where do they begin in VRAM? And the TA actually has to keep adding them, right? So as you feed geometry to the TA, it's going to keep making more and more of these OPBs in VRAM. And there's no limit to the amount of polygons that you might send to the TA. So they have a helpful thing called the TAOL limit, which is to say, if it tries to produce a OPB that would go beyond TAOL limit, it'll raise an interrupt. It's basically, you have too much stuff. I ran out of VRAM space. What do we want me to do? So it will write these OPB blocks, OPBs into VRAM in between these ranges. Similarly, the polygon data that we had sort of described here, we need to put that somewhere. So you feed ISP and TSP shading and rendering data to the TA, and it's going to copy it into a sort of standardized format for the renderer, and that will be placed in ISP base. And similar to the object list, it will not go anywhere above TA ISP limit, or it will raise an interrupt saying we ran out of space. So those are just used to configure, where will the data get stored, and a sort of like a safety limit to make sure that nothing that is not supposed to be overwritten, doesn't get overwritten. The next one is we need to set next OPB init. So you can actually independently specify TAOL base will basically point at the first OPBs for every tile, for every list in your screen that you're going to render. TA next OPB is where the next allocated OPB, I use the word TA with air quotes here, it's where the TA is basically going to get its next OPB. And then it's basically going to increment that address by the size of an OPB in order to point to where the next one's going to go. For using the TA, we also need TA global tile clip. So there is a sort of logical layout of how tiles are arranged in the frame buffer. All this register really encodes is my frame buffer is M tiles by N tiles. So 30 by 20, for instance, in the case of a 640 by 480. It's just how many tiles wide and how many tiles tall. So that needs to basically match for the TA to write into the correct places. TA alloc control lets you specify which list types are going to get written into and how many slots should actually be inside of each OPB. So the OPB in the picture above had, N entries. You can actually configure that. So for a list type that we're not going to render into, you can say it's 0. You can choose 32, 64, and I can't remember if it's 92 or 128. But basically, you can select for each list type actually how many entries will be in an OPB in order to try and minimize the overhead of the next block link control word to have as few of those as you can avoid. TA alloc control also lets you specify whether or not the next OPB is actually in a lower address or a higher address than the previous TA next OPB init. So basically, like if I have a block and it fills up and I want to create a new one, you can actually specify that it should go to a lower address or a higher address when allocated in the next one. With all of this, all of these set up, you can actually write to TA listeninit, which is an MMIO register on the GPU, and that will basically tell the TA to initialize. At that point, it's going to set up the initial OPBs and empty OPBs for every tile that you basically have described in these previous register rates. It won't render anything. We haven't prepared anything for rendering yet, but the TA is effectively ready to accept data at this point. Next is you're going to DMA, hopefully. You're going to basically send data to the GPU to actually render. So this works by DMAing the polygon parameter data to this address, which is memory mapped FIFO for the tile accelerator. The tile accelerator will keep processing data so long as it's fed. And once you send the last bit of data for once you send the last data for a particular list type, in the data that you send, you actually will specify on one of those pieces of geometry. It says like, I am the last thing of this list type. I am the last triangle strip of the opaque geometry, for instance. Once it reads that and it processes it, you actually get an interrupt out so that you know that you can, do whatever you need to do to react to that. After you've done all of the list types that you know you're going to render, the TA is done. Everything is ready inside the GPU for you to actually do your rendering. Also note there is something called list continuation that we'll describe in the future. You can basically, even though you had to input data in the order that I gave above, you can actually sort of do them in any order through something called continuation. but that's a subject for another video. Okay, so we have all this stuff sitting in VRAM. We've got the lists for each tile. We know how to kind of iterate through them and render each. We know what order we're going to render the tiles, and we can get to the polygon, coordinates and everything. How does rendering actually work, though? So when the region array entries are iterated, it goes through the OPBs. It gets to a parameter, a polygon parameter for a particular polygon. And it does different things, basically, depending on the list type. That's the point of having the different lists. The internal ISP and TSP, so image synthesis and texturing shading system, depending on the list type, they do different things. I mentioned this before, but basically the first thing that happens in the tile when we're processing that region array entry is if the Z clear was enabled, then a couple things will happen. We have 4 on-chip buffers, basically, that represent what we can store in the tile. And there may be more than this, but this is enough for us to describe. Clearing the Z depth will basically write a background depth value that exists in MMIO, ISP background depth. So this value will get set into every position in the 32 by 32 tile depth buffer. And then it will set a so-called ISP tag in the tag buffer here for the ISP background T MMIO register. So this register is basically a pointer to background polygon data. It's just like the data you'd normally send to the TA, except you explicitly tell the GPU, I want you to render this background data. So it's going to set a tag here, basically a pointer to that that background plane. So you can imagine this might be like it might be like a solid color or a gradient or something that you want to draw anywhere where there is no other level or character geometry or whatever. That's effectively what's going to get stored here. I'm very careful not to say render yet. So basically we've said how deep is the back of the scene that we're going to draw and what should we eventually render. These are basically just pointers to stuff. We haven't actually written anything yet. So what's going to happen, let's consider the case for opaque lists, right? So in the opaque list case, we're going to iterate over all of the opaque geometry, and we're going to compare in every pixel. These will all happen at once, by the way. It's going to literally have 32 by 32 units that all compute the depth of the triangle that's being rendered for every pixel in this tile, all at once in a single cycle. And then it's going to, again, all in parallel, check, is the depth here in the depth buffer, is it closer than the closest thing we've seen so far? So for the first piece of opaque geometry, that will basically compare this first opaque thing that we're rendering, is it closer than the background? Probably will be, right? And so what happens is it doesn't shade it or anything yet. All it does is update the depth. We found something closer. And it replaces the ISP tag, that pointer to which polygon it is, with the opaque polygon data, like a pointer to that triangle, basically. So it's going to do that, and then it's going to do it again and again and again and again. Basically, we're going to end up with is a depth buffer that has the depth of everything that's opaque, that's the closest opaque surface, and a 32 by 32 array of pointers to the things that we actually should shade. Now, because this is all opaque geometry, that's fine. There's nothing that is behind it that we cared about. So we only care about the closest thing. And now, if that's all we're doing right now, we're finishing opaque list processing, rendering, then we're actually going to do shading finally for the opaque geometry. And that will end up, let's say, in the primary accumulation buffer. I probably shouldn't have added secondary accumulation here. There's another buffer, you can do cool things. But basically, let's just say that I draw a whole bunch of opaque, colorful triangles. They're going to end up here in tile memory now. And if that were the end of rendering for this particular tile, so we didn't have any translucent lists to render or anything, then you could, and the flush bit was set, then this would actually get written out to the frame buffer at that point. So we didn't have any, if I had 1,000 triangles and they all landed, all of them inside this tile, it's not like I drew every pixel 1,000 times into VRAM. We're really only writing to VRAM the minimal amount. Let's consider the translucent list case. So for translucent, there's two different modes. There's pre-sort, where you already sorted everything for the GPU, and it's not going to do anything. In that case, it's kind of similar. So we will have already processed opaque geometry, because that's the order. It will generate fragments just like before, and then it will shade and composite all of those together, because now we have translucent material. We also need to blend the previous contents of the accumulation buffer with the new fragment that got shaded by the texture and shading engine. So it's very similar. It's just that we're not updating the ISP tag buffer here. We're just basically going to update the accumulation buffer and the depth buffer. Actually, maybe even the depth buffer is not updated. That's not a thing that we can actually take a look at from the outside for reverse engineering, but I don't know why this would need to update the depth buffer. Anyway, for translucent list rendering in the auto sort mode, where you say, GPU, I want you to render all of these translucent materials and on a per pixel basis figure out the correct order to render them in so that the shading and blending all happens correctly. How does that happen? So again, we've already rendered all of our opaque stuff. But now what we're going to do is repeatedly iterate through all of the translucent list data. We're going to find the furthest away surface in the list that is closer than what's currently in the depth. So that's basically what is the furthest thing that we haven't shaded yet. It will render that, and then it will blend it into the accumulation buffer. And the depth has been updated in this case. So now when we go through the whole list again, we'll find the next furthest away thing that we haven't shaded yet. And in this way, every iteration will basically draw one thing closer, one thing closer, one thing closer, and it'll draw from back to front. You can imagine this is actually really expensive. It's an incredible feature, and it's fine for a lot of things, and it's used in a lot of games. But you should know that pre-sort is much faster than auto sort. But that is an amazing feature, and it wouldn't be, basically 20 years really until this is done in modern GPUs at all. Okay, a few more details. Actually, this is the last bit of our first part, I guess. So we rendered all this stuff into the tile memory that you saw over there in the last slide thing. There's a few more things. So Framebuffer write control is an MMIO register that will control the color format that the accumulation buffer actually gets written back into VRAM using. It's possible to control a whole bunch of things. For instance, if you're writing into a color mode that is ARGB 15555, what is the alpha? You only get one bit. It's possible to basically specify in here any alpha in the tile in the accumulation buffer that's greater than a particular threshold that you set in write control, then it should be treated as full alpha. If it's less, then it should be made 0 alpha. So you can actually have a little bit of on-off alpha. Framebuffer write line stride will let you specify the number of bytes in multiples of 64 bits that are actually between a line, line n and line n+1 in the frame buffer. Where's the frame buffer actually located in VRAM is given by frame buffer write start of field 1 and start of field 2, soft 1, soft 2, and that's actually where we should be writing tile data out into the frame buffer. Those are just the beginning of the frame buffer, so that's why the combination of the positions inside of the region array entries and the TA global tile clip data give you enough information to figure out where would this tile be. Like one line of this tile would be where in VRAM, so that when it goes to flush that data back out into VRAM, where should it actually be located. And I haven't listed it here, but this is basically controlling where is the frame buffer written for a render. And so you would commonly see these, in commercial games or in homebrew. They'll basically update these before they call that start render routine. Correspondingly, in a vsync, you will typically see frame buffer read soft1, soft2, frame buffer read line stride, frame buffer read R control. Will tell you basically the display, the DAC, where can it find the frame buffer data that it should actually drop to the TV screen. So you'll frequently see these two, the read and the write versions of these, get flip-flopped as it does double buffering. So this is like the first time I tried to record this. Hopefully I get some feedback. You can let me know if this is ridiculous and what to improve. But yeah, that's sort of the high-level basics of the tile accelerator and data structures inside of the Dreamcast.